All right, just a quick video recap in case you're still struggling with the calculations from the lab, and also in this video is the sheet with the different possible metals for your unknowns. So remember, in our lab, we're heating up a chunk of metal in that little, metal jacuzzi, the little hot water bath we made. Get that metal nice and hot. The temperature of that water, right before we remove the metal from it, that's our initial temperature of the metal, right? We take that hot metal, we put it in the calorimeter with the cold water. We've already taken the temperature of that cold water. We've already gotten the volume, which would give us the mass of that cold water. Earlier, we got the mass of our metal. And we let that metal sit in there until the temperature stops changing. Once the temperature is constant, then we know that the metal piece and the water have reached thermal equilibrium. We can then get that final temperature, and that's T final for both. So through that experiment, we are able to get the mass of the metal, the change in temperature of the metal, the mass of the water, the change in temperature of the water. You're given the heat capacity of water, and all you have to do is solve for the heat capacity of that metal object. And again, the math that I'm showing here is all using that relationship of the net Q equals negative Q, right? The fact that whatever heat that's going into the water to change its temperature is the exact same heat that is leaving the metal. And we just give that leaving heat a negative sign, and the entering heat gets a positive sign. The negative sign ends up canceling out that negative temperature change that happens for one of them, giving us a positive value for C, which we need. So here was an example calculation that we did. In your lab write-up, it is giving you the opportunity to calculate them separately. So to calculate Q of the water on its own, then pop a negative sign in front of it to get Q of the metal. So you can do it that way, you can do it this way, it's all entirely up to you. Here is the list of the different metals that it could be. So take your pick from here, use both logic and your data. We're going to be chatting next class, tomorrow, about the lab write-up and the format that's going to take, and then we will actually be doing the lab write-up in class next time. So we'll be doing that on demand in class, so we'll be sure and chat about it, and any last-minute data that needs to get collected or whatever, you'll be able to work on that so that you can do that effectively on Wednesday. There isn't anything. I was like, percent error. I do want to go through the percent error calculation with you. So hang on just one second. All right, sorry about that. I had a little brief interruption. So yeah, I want to think there's into percent error. So percent error, there's a very straightforward calculation for it, just like with percent yield or percent difference or any of these percent values. We're looking at what we did experimentally versus what it should have been in theory or based on known records or whatever. So the equation for percent error is you want to take the value that is your experimental value, right, and subtract the theoretical value from it. So the theoretical value is the value it should be, the value you're getting from a data table, the value you're given, stuff like that. The experimental data or value is what you actually got in your lab, okay? So the experimental value minus the theoretical value divided by the theoretical value, and again, multiply that by 100. Now, technically, the equation has absolute value bars, so you can't have a positive or negative percentage, right? However, I like having the positive or negative sign because I feel like if it's negative, right, that means that our experimental value is lower than the theoretical value. So if you eliminate those absolute value bars, right? Just get rid of those. Or here, let me stop making it look ugly. If we just get rid of those and do it this way, we would see that a negative percent error would mean that we have a smaller experimental value than our theoretical value, right? So that negative would mean that experimental is smaller than theoretical. And if we have a positive percent error, then that would mean that the experimental is greater than the theoretical. And I think that that is useful information. So, the technical equation would have those absolute value bars. However, I like leaving it with positive negative because then we can see, are we too high or are we too low? And as we're trying to do our error analysis, as you'll see, you're going to want to investigate, is my number too high or is my number too low? Does that make sense with the errors that I was thinking that I had, right? Should my number based on my errors have been higher or lower or whatever? It's taking away some information, and I think it's useful information. So Again, technically there's absolute value bars, but I say ditch them and just use that positive or negative sign to say, hey, am I too high or am I too low? Then the percentage itself is really just how off are you from what it theoretically should be, okay? So that's how you get percent error, easy peasy, supposedly, and that's it, and I will see you in class next time. Good luck.